Hello there. This video is for section 6.2 on how to find volumes of regions that are rotated about an axis using the disk method. We're also going to do a problem about finding the volume of solid with any known cross-section, but that's just sort of related to what we're doing right now with the disk method. There are two main methods. One's called the disk method. One's called the washer method. Called the shell method. Disk and washer are kind of the same, but the shell method is the other type of way of doing it. And a lot of times students get a little confused about which is which method and what do I use when. So I try to make it simple. For the disk method, we are going to be slicing our region into infinitesimally thin rectangles, just like we did in the 6.1 video. We're going to be slicing things into rectangles that have an infinitely thin width. If those rectangles are perpendicular to the axis that we're rotating around, we're going to re-rotate it around some axis. So if those rectangles are perpendicular to the axis of rotation, that is known as the disk method. If those rectangles are parallel to the axis of revolution, that's called the shell method. So this we're going to be focusing on the disk method. In the next video, I'll teach you how to do using the shell method. But again, the thing that differentiates the two is the relationship between your rectangles and the axis of revolution. All right, let me get into an example so you can kind of see what's happening instead of trying to imagine what the heck I'm talking about. So for example A, we're going to use this method to find the volume of a solid formed by rotating the region bounded by these graphs around the line y equals 0. So when it says around the line y equals 0, that's the axis of rotation or revolution, right? That's the axis of rotation. So let me give you a picture of what this looks like. We have the square root of x graph, 0, 1, and 4. All right, so here's the square root of x graph right there. And we're doing x equals 0, which is starting here. We're doing, y equals 0, x equals 1, x equals 4. Sorry, so y equals 0. Let me draw in a y equals 0 graph for us here so we can kind of see what's going on here. Y equals 0 is this red guy right here. So we're going from this. We're also doing x equals 1 to x equals 4. So here's x equals 4, x equals 1. So this is my region right here, not this left-hand thing, because it has to be between all the graphs. And the graphs are square root of x, y equals 0, x equals 1, x equals 4. So the region has to be bound by all four of those things, not just three of those things. So the only thing which is bounded by all four is here, black on the left, red on the bottom, orange on the right, and green on the top. So it's this kind of shape right here. Boom, 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 boom. So this is 1, 0. This is 1, 1. This is 4, 2, 4, 0. So I have an idea of what that region looks like. And because I'm going to be showing my work on various assignments, I'm going to be showing my work on these lecture notes as well. So I'm going to just recreate a rough sketch of this region. All right, so I got my XY axes. That's how bad my memory is. 1, 1, and 4, 2. 1, 1, and 4, 2. So 1, 1, 4, 2, 1, 1, 4, 2, left, right, bottom, and then connecting like this. Okay, so that's my region. So I'm going to take this region and then I'm going to slice it up and rotate it around the axis y equals 0. So where is y equals 0? Y equals 0 is this bottom thing right here. So this is my axis of revolution. I'm going to put a little arrow here. So I'm going to be spinning this thing around the axis of revolution. Now, without thinking about chopping into rectangles, you're basically taking this shape right here. This is our sort of, shape in our region, if you can see over there. And we're going to be rotating around this y equals 0. This is where y equals 0 is on the bottom. So we're going to be rotating this. It's going to be a three-dimensional thing, right? It's going to be rotating around here. Can you see what kind of shape that makes? I mean, it's kind of like a cone shape. I think it's actually technically called a frustrum, if you want to know the fancy math word for it. But you're going to have basically this here making a kind of circular shape in three dimensions. And this goes two up, so it's got to go two down. I mean, it's symmetrical, right? Because it's rotation. So if it goes a two up, it has to go two down. So this is sort of a -2 in a way. We don't have to write that, but just to give you an idea of what's going on. And that's going to be some like circle, and all of this is rotated, so you get this kind of thing. So that's the three-dimensional figure we have here. When I rotate it around, I get this sort of bowl on its side, right? You can imagine tilting it, and it looks sort of like a bowl. So we're going to try to find the volume of that solid, of that thing, that region rotated around the y equals 0 axis. All right, but it's just complicated to do the whole thing. It's just a lot to work on. So once again, we have this idea, break it up into very small, thin, or very thin rectangles, find, in this case, the volume for one of those rectangles, and then add them all up. That's our standard process. So let's do that. Our region, which is, this guy right here, that's our region. We're going to take a rectangle. Now, remember, for the disk method, we want rectangles that are perpendicular to the axis of revolution. The axis of revolution is horizontal, and so our rectangles have to be vertical because that's perpendicular to the axis of revolution. So I'm going to draw just an example here of a vertical rectangle, infinitely thin rectangle. We now know from watching the 6.1 video, if you have, or doing the 6.1 exercises, that a very small width in the horizontal direction is going to be called dx. And then we need to find the height, which is going to be in the vertical direction, some y thing. It's the y to the top and the y minus the bottom. The y in the top is square root of x. The y in the bottom is just 0. So it's square root of x minus 0, or just square root of x. So that's the size of the rectangle. It has a height of y and a width of dx. We are not trying to find the area of the rectangle. We are using the slice of the rectangle to find what we're trying to find, which is the volume. So this little thin rectangle strip is going to be revolved around the axis, right? So this little thin strip right here is going to be revolved around the axis. You gonna work for me, pen? All right, one momento. Let me get my tech working again. Okay, my pen seems to be working now. So I'm going to be taking this rectangle and rotating it around, and I'm going to be getting this object right here. Which, if you can, I'm bad at drawing these things. So if you're bad at drawing these things, don't worry. I've been practicing it for over 30 years, and that's the best I got to. So do your best. But what do we get here? We are getting a disc. We are getting a circle that's filled in, right? Not just the outer side, but it's the whole, like this whole thing right here is the volume we generated for that. So a disc is a circle with a certain thickness. We know the thickness. We know the thickness is dx because remember our rectangle had this infinitesimally thickness of dx. And we need to find out the circle part times the width. So we need the circle times dx. So what is the area of a circle? The area of a circle, you may remember from your area of a circle, you may remember from your geometry, that's pi r squared, right? And then we're going to find the volume of this disk. And that's just going to be the area of the circle, pi r squared, times how thick it is, times the width, basically. We know what that thickness is. That thickness is dx because we sliced it in the vertical direction, making a very small thickness in the x direction. Pi is a number. We don't have to worry about that. And r is the radius, which is just the height of the rectangle. Remember, the radius goes from the axis of revolution all the way to the outside, right? Just like the radius of any circle, it goes from the middle to the outside. So our radius goes from the axis all the way up here. And that's just a vertical direction in the y direction. And we already know it's just the top y minus the bottom y, which is the square root of x minus 0, or just the square root of x. So our radius is square root of x squared, because it says r squared, right? So radius is square root of x squared times dx. And then we're going to be integrating this over all possible values. All possible what values? All possible x values. Because it says dx, we know we have to use x's. All right, so what are the x's? Well, the rectangles that we used started here at the left side of our region and go all the way over here to the right side of the region. That's our region, that we started with, right? From y equals square root of x, y equals 0, x equals 1, x equals 4. That was our region. So our rectangles go from the far left, which is where x equals 1 is, to the far right, which is where x equals 4 is. So this has to be from x equals 1 to x equals 4. So we took our region and we sliced it into vertical rectangles. And then we found for that particular slice, when we rotate it around, it forms the shape of a disk, and the volume of that disk is just the area times the width. The area is pi r squared, the width is dx. So we get pi times r squared times dx. The r is just the height of the function, which is the y value for the square root of x. And boom, we got our integral. And at this point, now we have like just some easy calculus to do. If it's not easy to you, that's okay. It will become easy as you do a lot more of it. All right, so let me just kind of finish this up a little bit. 1 to 4, these got to be x values. The pi I can just leave on the outside because it's a number, and when you multiply by numbers in derivatives or integrals, it doesn't affect anything. They just get multiplied by the end. Square root of x squared is x. And then I get my lovely dx in there. I do my antiderivative. The antiderivative of x is just x squared over 2. And then I get my x equals 1 to x equals 4. And so I got a pi times a bunch of stuff. I got to plug in the 4, which is 16 over 2. I got to plug in the 1, which is 1 over 2. I guess I don't need that much space. So there's when I plug in the 4 and the 1, and then I have to subtract. So this is 8 minus half, right? Which is 7.5. So this is, or I guess 15 halves. I'll just leave it as improper fraction because math people like improper fractions better anyway. So 15 pi over 2 would be the volume. This is the volume of the disk was pi r squared times the thickness. The volume of the whole thing was the integral, right? When we integrate, we're adding all the possible disks together, and that will give us the total volume. So the total volume is 15 pi over 2, whatever the units are, some cubic units, depending on what x and y are measured in. All right, so that's the disk method, at least for this basic problem where I had this simple region. We'll do some more complicated ones, and that's sort of the idea of 6.2. At the end, I'll also do one in which I will not do just a standard rotation, but I'll do some sort of defined cross-section so you can see how to do it and not be locked into always doing pi r squared, because quite frankly, it's not always going to be this shape, right? It oftentimes is, but not always. All right, let's move forward to example B. All right, use the disk method to find the volume of the solid formed by rotating the region bounded by y equals square root of x, which is the same one before, but we also have y equals 1/2 x, and it says around the line y equals 0. So we're going to have the square root of x function. We also have this 1/2 x function, and those are the only things that are bounding the region. So we don't have like 4 things anymore bounding the region. We only have 2 things. So again, we need to see what that looks like so we can try to figure out what region we're talking about if it's only bounded by these 2 things. So I got my square root of x. Let me get rid of the other stuff here. And I need my 1/2 x. So square root of x and 1/2 x actually did say y equals 0 was the rotation, but I won't put that in there because that's not part of the region. So what's bounded by these two things? You can probably see it. Some of you can. It's this region right here. This kind of curvy thing on top, a flat thing on the bottom. If you saw the video in 6.1, these may look familiar. We did one like this before. So it goes from 0, 0 with a straight line thing here all the way up to 4, 2, and the curvy thing on top. The curvy thing being the square root of x. Okay, back to my lecture notes. Recreate a rough picture so that the reader can see what the heck we're doing. Sorry, I gotta get going back. 0, 0, and 4, 2. 0, 0, 4, 2. 0, 0, 4, 2. There is a straight line thing going this way. There's a curvy thing going this way. That's our region. We are revolving it around the line y equals 0. It's around the line y equals 0. Y equals 0 is called the x-axis. This is y equals 0. And revolving it around y equals 0. So we're going to take a slice of our region, which is perpendicular to this axis of revolution. Our axis of revolution is horizontal, which means our rectangle has to be vertical. So once again, we're going to make a vertical slice. Boom, boom. All these vertical slices go between these two functions, the one over here on the far left, everything in between, all the way up to the right. They're all spanning this top part minus the bottom part. The top part is the square root of x function, and the bottom part is the 1/2 x function. So we know that the height of a rectangle goes between two things, between square root of x and 1/2 x. And as we know, to find the distance between two things, we just subtract. Okay, so what's going on with this thing? We're not trying to find the area of this region. We are revolving this thing around. Now we're only revolving this top region, right? This top thing, not the bottom thing. So what happens when we revolve this top thing? We get this sliver thing here and we're rotating it around. So this little piece is going to rotate around here. This little piece is going to rotate, like if it was 2 up, it's got to go 2 down, right? It's got to be down here. This curvy part's got to be this curvy part right here. Straight line parts. So it's just a mirror. It's a mirror image. But then because it's rotating, it's going around. And the way I've learned to draw this is just to kind of draw like little circle things. So like this thing. And for our example slice, this little slice is going to be going over here. It's going to be like this, but it has a hole. It has like a missing part in the middle. Let me not use all green because it's just getting confusing. Let me use another color like blue. So here's my little region. The outside of my little like rectangle goes there. The inside of my little rectangle goes here. And my region is, or my volume is this little disc right here with some very, very thin thickness. And the thickness is in the x direction. So you may now know that that's a dx thickness. So we get this sort of, it's not a disc because it's got a hole in the middle missing. But a disc with a hole in the middle is just a big disc minus a little disc, right? So we're just trying to find like the volume of the whole disc minus the volume of the hole, and that will be the volume of this washer. This is called a washer, or some people call this the washer method. It's really still the disc method. We're just going to be taking the entire disc minus the hole in the middle, that missing part in the middle. Let me draw this again, just without all of the stuff here in the way. So this is my little rectangle here. I'm revolving it down here. I get this hole in the middle. I get this sort of outside part. This is my volume thing here. It has a very small thickness, dx. So I need to find out the volume of the the outside stuff and subtract the volume of the inside stuff. Our axis of revolution is right here in the middle. That's our y equals 0. That's important because radiuses always measure from like the center to the outside. All right. So what is the total, the total disc volume for the total. Oops, volume for the total. This is really the outside, right? So this is the outside one. So it'd be the volume including the whole. So it's the volume of like the whole thing, right? Volume of the whole thing. All right, so well, we know how to find the volume of a disk. That's just pi r squared times the thickness, right? That's how we found the volume in the previous problem. So for the outside volume, the radius goes from the middle. Radiuses always go from the axis of revolution or from the middle all the way to the outside. So we're actually not needing to subtract two y values for this one. It just goes from there all the way up to here, which is the y equals square root of x graph. So the y height here is square root of x. The y low here is y equals 0. I subtract those two things. Square root of x minus 0 is square root of x. So this is going to be pi times square root of x squared times the thickness, which we know is dx. Now we need the volume of the volume of the whole, right? So the volume of the whole, that's a disk with the inside. The inside is going to be where the hole is. That's this part inside. That's the hole that I have to subtract off because I don't want to find the entire volume. I want to find just that volume that's there in blue. So I need to subtract off that hole. But it's a disk. And so we know how to find the volume of a disk. It's pi r squared times the thickness. In this case, let me move this up a bit. So in this case, let's get rid of this black thing for a moment. The inside thing is going to be here to here. So to find that vertical distance between two things, I have to subtract the top one minus the bottom one. The top one is this function, 1/2 x, and the bottom is 0. So the radius is just 1/2 x squared because it's radius squared, right? Remember, we're just going for this bottom part, and the bottom part is for the bottom function. That's y equals 1/2 x. So it's pi times that interior radius squared times the thickness, which again is dx. And that would be the volume of that inside hole. So what is the volume of this thing we're looking for? So our volume is equal to the volume of the outside minus the volume of the inside. Volume of the outside minus the volume of the inside. And in this case, we know the outside one is this guy right here. So pi square root of x squared. I'm going to leave that there just so people can follow my work. I mean, obviously it's x if I square it out, but I'm going to leave it there. Minus this guy, pi times 1/2 x squared, which is 1/4 x squared. But again, I'll leave it just unsimplified form like this, dx. And that is for the slice. If we're going to be finding it for all possible slices, we just integrate from the smallest x value to the biggest x value. Because it's a dx, we need everything in terms of x's. So for our region, the smallest x is over here at 0. And the biggest x over here, that's the endpoint where our region ends, is x equals 4. And so that's our integral. Now, the mathematician will try to like make this like look a little nicer. Since there's a pi in both things, they will factor a pi and put it on the outside. Right? Since there's a dx in both things, they're going to factor it and put it on the right side. And then, of course, they'll do square root of x squared is x. And 1/2 x all squared is 1/4 x squared. And that's how you would see it written out by a math person. That would be the two things subtracted times the width dx, integrated from 0 to 4, and then multiplied by pi because of our pi r squared formula. All right, you get all that? These are these where it's getting hard, where you get this sort of outside minus inside thing, like a washer. It's still pi r squared, but you're gonna have to figure out two pi r squareds and subtract the two of them in order to get the result. As you may know from my previous comments and my previous videos, I'm not a big fan of actually working everything out on these videos because it just takes time, and I think people want to see more of the new material than just calculations. So I'll do minimal stuff. The antiderivative of x is x squared over 2. The antiderivative of x squared is x cubed over 3. And then I have to plug in these values of 0 and 4 into this crazy thing, and then I subtract. So, I plug in the 4, I plug in the 0, and then I just do the math, do the arithmetic basically to get the result. And I guess it's 4 cubed over 12 minus, when I plug in 0, those are all 0 anyway, right? So it doesn't really matter. And all of the stuff is times pi. All right, I'm gonna let you do the math on that one. It's not very, very difficult at this point because like the second part's all zeros, and you get hashtag or number. So you get a result for this, and that's going to be how to find the volume of this region revolved around the y-axis. All right, let me see if I can scroll out a little bit so you can see my solution. There we go. So drew the region, imagined slicing it into a very small rectangle vertically, which is perpendicular to the axis of revolution, rotating that around, getting this washer, this disc with a hole missing or a hole on the inside, right, that I have to subtract off. I drew it again just to make sure people kind of see what's going on here. I need to do pi r squared for the outside part of this disc, and then minus pi r squared for the inside part of the disc. And that's this, outside part minus inside part. And then I just did the math. All right, well, we got some more examples to go through here. Okay, so that's B. All right, so I think I have 3 more examples for this one to try to get people to understand what's going on. My last example is going to be a different looking one a little bit, but uses the same technique. It just kind of, you haven't seen it before, and you've totally got this. You might still want to check out the last example, which would be CDE, example E, if you want to skip that. I don't know the timestamp. I am going to do one in which we are rotating around like this way. We're going to be rotating horizontally, right? Like this. So it's going to look a little bit different because we're going to be slicing our region a little bit differently. And so I want to show you a little bit what that looks like. All right, so here's some more examples. And I'm going to try to pause the video for a moment because my cat is just meowing and she wants something for sure. I'm going to find out. Okay, I'm back. So ready to do example C, using this method to find the volume of a solid given by a certain region. And we're going to revolve it around y equals 0 and also around y equals 2. So once again, I want to see a picture of the region of x and x squared minus 8x plus 16. That's these guys right here. So the only thing that's bounded by these two graphs is this little shape right here. And let me see if there's anything else. Oh, x equals 3 and x equals 4 are also parts of the bound. And I'm revolving around the y equals 0. So let me draw in the 3 and the 4. Here's 3, here's 4. So, okay. So the only thing that's bounded by these guys, and the red one is actually kind of distracting because it's right there is where 3 is. Right? So that's the 3, and there's the 4. And so we get this region right here. If I put the red one back, so it goes from the red here to the blue to the orange to the purple. So it's this region right here. So we have this point here, 3, 1. We have this point right here, which is 4, 0.25. And we have 4, 0. So that's our region that we're talking about. Let me try to recreate that. 3, 1, and 4 3/4. X, Y axis. 3 comma 1, 4 comma a quarter, or I mean 3/4. All right, and then we had, let's see what the shape looks like. We had a really U-y type thing, but it only stops here. It doesn't go all the way over there. So again, we're only focusing on 3 to 4. So it just goes down here like a side of a parabola, which it is, I guess. And this one is a little curvy towards the top. What did I just do? All right, I gotta figure it out. Hold on a sec. Okay, I accidentally closed my little lecture note program here, so I don't know if the scale changed. It probably did. So this thing here, and then we had like a parabola type thing, like this, and then we had a side like this. So if you didn't remember, it's this region right here. We got this line, we got this parabola, we got this thing. Let's see if I recreate it. I think I recreated it okay. Okay, and then we're going to rotate this around the line y equals 0. Y equals 0 is fancy name for the x-axis. And I'm going to be setting up these integrals, but not really doing a lot more of them because you guys know at a certain point, it just becomes routine. We're going to slice this thing perpendicular to the axis of revolution. That gives us a dx again. We're going to rotate this thing around. That gives us a washer again with an outside radius and an inside radius. Remember, this goes like up like 1, it goes down 1 or whatever, right? Like it's a mirror image, right? So you can draw a mirror image if you're getting stuck on how to make it look semi-decent. So the volume of the slice of our little rectangle revolved is going to be the volume of the outside thing minus the volume of the inside thing. And that's going to be our like disk method or washer method, if you prefer to call it that way. And then we're going to be integrating it to find the volume of the whole thing. So the outside thing, well, the outside has to be like the big radius. So the big radius goes from the axis of revolution, which is right here at the y-axis, all the way up to the top, which is this top graph. I didn't label them, unfortunately. Let me label them now. This is the 3/x graph right here. And the curvy one down here was the parabola. Maybe I should call them f and g again, like I did in the previous video, just so I don't have to write so much. This is my g function over here, and this is my f function over here, just so that I don't have to write so much and it looks messy. So for the outside radius, I need to find the distance from the axis of revolution, which is at 0, all the way up here to the function. So that's going to be the y value for the function minus 0. So just the y value for the outside function, which is the f function, which is 3/x. So we get pi times the radius squared times the thickness, which is dx. And then we're going to subtract off the volume of the inside guy, which is still going to be like a pi r squared times dx. But now we just have to find the inside radius. The inside radius is this little hole right here. This part right here is the inside part that we're not including because that's not part of our region. Our region stops right here. So this is where the hole begins. So that height, that y vertical distance, is used as determined by the g function. So I need to find the y value of the g function minus 0, just the y value of the g function, and that's the radius of the hole that I need to subtract off. But the g function is right over here. So I just subtract off, well, I guess I didn't give myself enough space, but that can be fixed. So the g function is x squared minus 8x plus 16. And it's got to be that thing squared because it's pi r squared, right? And the r, which is the g function, right? That is already x squared thing. So when I square this out, I'm going to get x to the 4th at some point, right? Again, I can take the pi outside, but the volume in total, so the total volume is just going to be the integral of all this stuff. It's just the integral of all of this stuff. And we're adding up all the possible slices, and that will give us the total volume, not the volume one slice, but the volume of every single slice. We are doing things in terms of dx. So our limits have to be in terms of dx, or in terms of x. So all these little rectangles, they go from like here, all the biggest possible rectangle is at x equals 4. The leftmost rectangle is at x equals 3. So this is 3 to 4. I can stick the pi on the outside. A lot of math people do that. 3 over x squared is 9 over x squared. And then this guy is, I have to square it out. So I have to square out a trinomial times a trinomial. And I don't know a lot of people who are good at doing this in their head. So yeah, I mean, this is a calculus class, but you're gonna have to use an algebra. So over here on the side, I would write out x squared minus 8x plus 16 times x squared minus 8x plus 16, and then distribute, right? Multiply x squared times x squared, multiply x squared times 8x or minus 8x, x squared times plus 16, and did the same thing with all the other ones, right? Just everything in the first thing multiplies to everything in the second thing. And I get some crazy stuff. I mean, I'll write out some of the stuff. I get x to the fourth minus 8x cubed plus 16x squared minus 8x cubed plus 64x squared. I don't even know what 8 times 16. I think 8 times 16 is 120 something. I don't know. I'll just write it as 8 times 16 minus 8 times 16x. That's this guy times this guy, by the way. And then 16 times x squared, which is 16x squared. I get another 16 times 8, so minus 8 times 16x. And I get 16 times 16, which is actually 256. I do remember that one. And that's this entire thing is what goes in here, right? That's this entire thing here. That's squared out, right? And then again, once you do the algebra, then you just do the calculus, you do antiderivatives. This is x squared or x to the fourth minus x cubed, blah, 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 256. Make sure to use your parentheses so that your negative gets distributed properly. Do the antiderivatives, plug in 4, plug in 3. And after all that tedious calculation, you get your answer. You get a number, which is going to be called the volume. Do it yourself. Do it. Do it. You can do it. You can do it. All right. So I'm going to leave that to you and to calculate the exact value. All right, but what about the second part of this problem? I did mention it briefly, but I didn't emphasize it. This is finding the volume of the solid formed by this region around the line y equals 0, but there's a follow-up. What if we revolve it around like y equals 2? So our axis of revolution is no longer y equals 0. Our axis of revolution is y equals 2. Okay, so same region, by the way. I'm going to draw the region over here on the right, just so I have some space. Maybe I don't have a lot of room in the right. Well, I'll see what I can do. All right, so that's as far right as it'll let me go. So I need to draw this region. It's the exact same region, so from 3, 1 to 4, 3/4, that kind of thing. Y equals 2. Is it y equals 2 or y equals -2? I thought I had done in my notes, I thought I'd done -2. Yeah, it says y equals 2 here, but I really want to do y equals -2. I hope you guys don't mind. I just changed that to -2. I'm going to do another one like y equals 2 later on, but the y equals -2 is a little easier. And I think when I typed out these lecture notes, I forgot -2. So I'm just going to change it on the fly because I think that's an easier one for me to explain and for you to grok. So I'm going to start there. Anyway, so we're going to go y equals -2 just to make things a little bit easier to follow. But we do get the same region, so blah, blah, blah. That's the start of it. Again, I have to remember. I'm going to zoom out so I can see it more quickly. All right, so it's 3, 1. Okay, so 3, 1, and then 4 and like 3/4 or something up here. And it's kind of goes downish like this, and it goes down like this, and it goes, oh, it doesn't start from there. It starts from here. It starts from right here. Goes like that, or like that, like that. So that's our region. All right, so that's our region, same region as before, right? Same region with the graphs 3 to 4 for the x's. And now, according to my update here, we're going to revolve it around the line y equals -2. We can also do 2, and I'll do one like that next time on my next example, but I'm going to do -2 for this one. So again, apologies for not typing it in correctly, but I wanted to show you y equals -2 as our axis of revolution. So I'm going to draw on my axis of revolution. We're going around this thing right here. And this is where it starts getting a little bit more confusing, but we're going to use the exact same slicing method every single time. All right, so I'm going to take my region. I'm going to do a little slice. I'm going to revolve that around the line y equals 2. This is 0, by the way. This is the y equals 0. This is the one that we revolved around previously. That's where 0 is. We're going all the way down to -2. So this is where our center is. This is where the middle is. This one up here is like more, almost quite one away. So if I go down to -3, the mirror image of this guy will be having there, and the mirror image of this is 2 away. So at -2, we get this one. So this is 0. It's 2 away. Oh, 2 ways at -2. So let me try this again. All right, I want to get this right so that you guys can see what's going on here. Let me start with the bottom part of the rectangle because I think that's where it would be easier for me. So at the bottom part of the rectangle, it is a distance of 2 away from the axis of revolution. From 0 to -2 is a distance of 2. So if I was going to do a mirror image around this axis, then 2 more down here would be the bottom of my rectangle, right? If it's 2 up there to the axis from the axis of revolution going up, it's got to be 2 going down from the axis of revolution going down. So my rectangle, the bottom of my rectangle has got to be there. The top of my rectangle has to be further up. If it's mirror image, it's got to be further down. So my rectangle ends up being down here. All right. So the top part of the rectangle is 1, 2, almost 3 away from the axis of revolution. So I have to go 1, 2, almost 3 away from the axis of revolution, going down. All right, so that's what my sort of, mirror image of the rectangle is. Let me connect things together. So I'm going to have this hole in the middle. That's the part that doesn't count because our region is right here. We're going to do this thing right here. So this is my disk, right? It's a big disk with a hole in the middle, so a washer technically. And then we're going to set up the integral for this thing. Okay. We almost got it. Trust me. You may think it looks complicated. We almost got it, really. Like any of these problems, to find the volume, we're going to do a volume of a slice, and then we're going to subtract off, the big part or the outer part minus the inner part. So the volume of a slice, we're going to do the volume of the outer part minus the volume of the inner part, or the inside part. So what's the outer part? Well, the outer part is going to be the big radius. So the big radius goes from here, from like the outside to the inside, or actually, I guess technically from the axis of revolution, from the middle all the way to the outside of the region. So that goes from y equals -2 all the way up to this top part. And what is that top part? Well, if you remember from our previous thing, that's the f function. That's the 3/x function. So right here, scoot over there, this is my f function right up here. So I think I drew this. Did I draw this wrong? I forgot to draw part of my picture. I don't think it matters much. but you notice that I did forget this little part right here, this little like parabola part. So let me update that real quick in my picture. It's not going to change our method or what we're doing because the picture is just a visual aid. But for people who are getting a little confused, I want to fix that so that you're not so confused. So there's my little parabola part. My rectangle is still here. It's still the outer part minus the inner part. It's still the same thing. Okay. So make it look a little better. So our rectangles, do this thing. Okay. So the outside volume is I have to use the distance from the axis of revolution all the way up to where the outside radius is. And so that distance is from F, from that Y height down to -2. So there's several ways you can think about it. You could just do the standard thing to find the distance between two things. You just subtract. So it's the F thing minus the -2 thing. Or you could just say, normally the Y distance would be to 0, and then I have to add 2 because I go 2 below 0. So either way, you're doing the F plus 2, either by subtracting -2 or just by saying that it's going to 0 and it's going 2 more. So the outside is going to be our outside radius. Our outside radius here, just to remind you, is 3 over x. So this is 3 over x plus 2. It's minus a -2 or plus 2. That's my radius. I got to do pi times the radius squared times the thickness. Thickness is dx because we've sliced it vertically, giving us a very, very small x width. The inside radius, well, that's going to be a pi r squared again. So that's going to be the r and then times the thickness. So what is the radius for the inside one? Well, this may look familiar because we did it before, right? If you can look at this part, we had the 3 over x squared was our radius for the outside, and the other one, which is the x squared graph, was our radius for the inside. It's going to be the same here, right? We have this graph here from the middle going up there. The difference is I had to add 2 because the outside radius doesn't go to 0, it goes to -2. So the inside radius doesn't go to 0, it goes to -2. So it's going to be the exact same thing. It's going to be this x squared thing. And then it's going to be plus the 16, sorry. And then it's going to be plus 2 minus -2. So that's the volume of a slice. And to find the volume of the whole thing, well, we just need to integrate. So the whole thing here is if you can slice up the region, find the, in this case, volume of that slice, and then integrate, we get the volume of the whole thing. So the volume of the whole thing, excuse me, is going to be, we'll put the pi on the outside. We got this 3 over x plus 2 squared. We have minus this guy right here, which is x squared minus 8x plus 16 plus 2, which of course I can just write as plus 18 squared. And then all this stuff here is dx. So there's my pi r squared and my pi r squared. Let me make this look a little neater. It didn't come out very good. So 3 over x plus 2 all squared. So that's your pi r squared for the outside minus pi r squared for the inside times the thickness, which is dx, integrated from the smallest x value to the biggest x value. It's the same region as we did before. Just like we did before, the smallest x value was 3 and the biggest x value is 4. You can see that in our previous one. So this is going to be x equals 3 to x equals 4. And then I'm not going to do the rest of this. That's, again, you could just square things out. It's kind of a pain of algebra, but, welcome to math. It's kind of like do a bunch of math stuff and then get the answer if you don't make any mistakes. So there's an example where the axis of revolution was down 2. So we just couldn't do like our normal pi r squared. Our radius actually had to be 2 bigger each time because the axis of revolution was actually too further away than it was before. At -2, it was a distance of 2 more than before. Okay. So we're gonna do another problem. this way. This time we're going to slice it the other way. I've made it obvious by putting things in terms of x's, but really that's not the determining factor. The determining factor is your rectangle has to be perpendicular to the axis of revolution. So let me show you why that's going to be the case for this problem right here. So we get this x equals 2y squared and x equals y cubed. So let me get rid of this painful other graph and go to these guys, x equals 2y squared, x equals y cubed. That's this little skinny region we've done before, going from 0, 0, and this point over here is 8, 2. Zero, 0 to 8, 2. And we get a thing on the top and a thing on the bottom. And it's kind of like a skinny little thing. That's our region right there. The thing on top, let me just double check. So if I click on this red thing, you'll notice that Desmos shows me the red thing right here is it's kind of highlighted y cubed. And the one on the bottom, now it switches over to the highlight. And this one is the black one. It's 2y squared. So x cubed is on the top. So let me go back and show that. So this is on the top, x equals y cubed. And on the bottom, we have x equals 2y squared. All right, so that's our top and bottom. And we are revolving it around what axis? Around the y-axis. The y-axis has the equation x equals 0, by the way, but we know what the y-axis looks like. This is the y-axis right here. So this is our revolving around the y-axis. So according to the disk method, if we are revolving around the y-axis, then our rectangles have to be perpendicular to the y-axis. So I need to draw a rectangle which is perpendicular to the y-axis. The y-axis is going this way, so my rectangle has to go horizontal, has to go this way. And then I'm going to rotate this around. I don't know if I gave my stuff enough room. It looks like I didn't. So I'm just going to pretend that this is the rectangle over. It's supposed to be symmetric. It's not exactly symmetric, but I'm cheating a little bit. I'm not sure if that's good as a teacher. Maybe I'll cheat this way. Maybe I will like change my region a little bit and make it like a little closer like this. I think that's a better cheat. Like this. And make 8 over here. Okay. So just to make it like appear a little bit scrunched in. Okay. So therefore, when I need to change this region, so I break up my rectangle now here. Come on, Jim, you can do it. You can do it. You can do it. Here's my horizontal. Then the distance from here to the axis of revolution should be the same distance, right? The idea is it's a mirror. If you're revolving around this axis, then it's going to be mirrored onto the other like side, right? So that is a better representation of like the mirror image on the other side. We have this inside hole. We have this outside like part. So the hole is missing. It's missing. Well, that's what a hole is, right? Okay, and the outside is the region we're looking for the volume of. Now notice because we slice this thing horizontally, you can see my little green rectangle there. I'll get rid of these little red marks, but you see my green rectangle. It's a horizontal slice. The thickness of this horizontal slice is a small change in the vertical direction. And you may have an idea what that's called. That is called dy. dy is the thickness. Because dy is a thickness, everything that we do has to be in terms of y's. Because the dy, the differential, is going to determine the variable for the integral problem. All the variables have to match. You're going to have to match the dy or do some sort of miracle to get rid of dy and change it as some other variable. We're going to do that in chapter, I think, 10, but not now. We're just focusing on making everything look like a dy. But, we just do a pi r squared thing, right? We do the pi r squared of the outside guy, pi r squared of the inside guy, subtract them off, and we're good to go, right? So let's just do it. Let's just do it. So we need pi r squared for the outside guy minus pi r squared for the inside guy, right? And then we need to multiply by the thickness each time, which is dy. And eventually we need to integrate from the smallest y value to the biggest y value in our region. And that would be how we find the volume. Getting the idea? I mean, once you have this idea of slicing and then finding the stuff and then adding it up by using an integral, the problems start to really feel like a lot of the same stuff. You just got to, slice it, find the stuff, in this case, find the volume, and then add it up. Maybe that sounds a little simplistic, but I have been doing this for a long time, and I now have done enough of these problems to see that it's the same concept each time. All right, let's actually do it. The smallest y value, the lowest y value is down here. Our region is in black, just to make sure our region is right here. So the lowest y value is right here. That's the very bottom of our region. That's where y equals 0. And the highest y is right up here. That's where the highest y is, and that's at 2. So we're going to go from 0 to 2. All right, I'll stick the pi on the outside because that's traditional. I get to find the outside radius. The outside radius, my friends, goes from the farthest x value to the axis of revolution. So it's that distance right there. It's a horizontal distance. Horizontal distances are always measured in terms of x, right? So it's the big X. It's the function. Well, it's this function, right? This is the big X function right there, right? So it's the X big function. So I could write the big X here squared dy. But everything's got to be in terms of y, right? You can't have some things in terms of x and some things in terms of y's. So most people wouldn't write x big there. They would just write the equivalent thing in terms of y. So what's equivalent to the x big thing? Well, we can see the formula right there. The formula is 2y squared. So the x thing for the big one is just called 2y squared. That's what the formula says, is x is 2y squared. So that big X is 2y squared. And then we get a dy in there. I'll put the dy over here. Remember, I got to subtract off the pi r squared for the inside one. And that's going to be the little x, right? The small x. And so the small x is going to be, well, it's going to be from here to the axis of revolution. From the axis of revolution right here, for at x equals 0, all the way over here. That's going to be the distance of our hole that we have to subtract off. That's just going to be the small x value, right? So that's going to be the small x value. And the small x value is for this other function on the other side, which is y cubed. So it's going to be y cubed squared. Y squared because it's pi r squared, right? I kind of like to put the pi's over here. I track about what I'm doing, but people say, why are you doing the pi there? So people complain when I put the pi there. You get to do what you want to do. It's pi r squared minus pi r squared. It's the outside minus the inside. And that's how you do all these sort of disk problems when there's a hole in the inside. Now, everything in terms of y, right? I got a 2y squared and a y cubed squared and a dy and a y equals 0 and a y equals 2. So now I just do the calculus. At this point, there's really not a lot. I'm going to do the math. There's a lot more calculus to do at this point. You just have to do the math. So you get the pi, you get to 4y to the fourth, or maybe, I'll do it that way. Some people put the 4 in front of the pi. I don't care. This one is y cubed squared, which is y to the 6th, so pi y to the 6th. And you get a dy, and then you anti-differentiate, etc. Right, you get a pi, you get 4y to the 5th over 5, minus pi y to the 7th over 7. You evaluate it by sticking in 2 for y. You subtract when you stick in 0 for y, and you get your answer, which is the y. Okay, that's how you do these kind of problems. Now, I promised I would do like a harder, like non-standard axis of rotation. So this is the one where I chose something which was like not further away, but on the other side. So the other question, the second question I have is, what if you do it around x equals 10? So we're not doing it around x equals 0. X equals 0 is the y-axis. I'm going all the way over here to 10, and I'm revolving it around 10. So let's do that. Let's just set it up and see how it works. Again, it's going to be the same process. Let me just draw it out. boom, boom, 0, 2, 8, boom, like this, right? And our axis of revolution is at 10, which is over here. Perpendicular slice to the axis of revolution. dy is my thickness. Well, that was a very, not very thin slice. I'll pretend it's thinner. dy, vertical, thickness is dy. Take this thing and revolve it around. So the distance from here to here has to be the same as distance from here to here. It has to be the same distances. So my rectangle goes like this. The inner part of the rectangle has to be the same distance. The outer part has to be the same distance. And then get rid of all these sight lines here. So that's where my image of my little rectangle slice is. And then I'm going to revolve it around. That's my disk with a hole missing. So I'm going to do like pi r squared minus pi r squared. And that will give me the volume. All right, so we need an outer radius, inner radius. You notice the middle of this circle is right here. So if I'm going to do the outside radius, I have to go from here to here. Let me do it in maybe blue. So from the center all the way to the outside of the big part of the circle, that would be my big, radius, my x big. So I'm going to do pi times the big X, pi r squared times dy, minus the same thing, but with a small radius, pi x small squared dy. And then I'm going to integrate all of those from the lowest y value or the smallest y value to the biggest y value. We know the smallest y value is 0, the biggest y value is 2. Everything's got to be in terms of y, so all these x big and x small have to be in terms of y. Let's do x big. So x big goes from here to here. Well, 10 is the bigger number, so it goes from 10 all the way to here. What is this thing here on the left? What is that guy? What did we write that as before? That guy on the left was x equals y cubed. So how do I find the distance between two things? I subtract. But you may remember you subtract the bigger one minus the smaller one. The bigger one is over here. It's a bigger x value. Remember, x values get bigger and bigger to the right. So this is the bigger x value. That's the smaller x value. To find the distance between two things, I subtract. So this distance, this x big distance, the radius in the big direction, is going to be the subtraction between those two things. So it's going to be 10 minus y cubed. That's my radius for the big function. What about for the small one? For the small one, I'll use red. I go from the center to here. Well, where is here? Here is given by this bottom function. What's the bottom function again? Oh, it's 2y squared. So this one here is x equals 2y squared. So it's going between 10 and 2y squared. That's the distance in the x direction. That's the small radius, right? So we need to find that distance from 10 to that function, x equals 2y squared. How do you find the distance? Well, you subtract the big one minus the small one, which is going to be 10 minus 2y squared. That didn't look like a y. 2y squared. And then our thickness is dy. And there you go. That's the integral to find the volume of this thing, which was revolved around x equals 10, which is as hard as these problems get, really, right? We had some weird region. We're slicing in a way which may not be comfortable. We're revolving in a region around an axis, which is not standard. But the method I'm just trying to show you is consistent. Hopefully that's getting across, even if you don't feel comfortable or confident doing it yet. Hopefully these examples are giving you an idea of how to approach it, how to draw it out. If it's a disk, it's just pi r squared times the thickness. If it's a washer, you have to subtract off the inside part. So pi big radius squared minus pi little radius squared, each of those being multiplied by the thickness, which is either dx or dy, depending on the direction you sliced the rectangle. I know it's been a really long video. I have one example, and it's a short one at the end. It is the one where we're not actually getting these discs. We're getting some other shape. We're getting a known cross section. So let me show you this. It will not take as long as the other ones, I promise. I have a region. Actually, you may have seen these equations before. Square root of x, 1/2 x, x equals 1, x equals 4. I think that may be x equals 0 and x equals 4. Let me pause the video real quick and double check my notes. I'm going to say 1, so we're going to go with that. So let's just do it. So let's find out what that looks like. Square root of x and 1/2 x are ones I've done before. So square root of x and 1/2 x, that's this region right here. And we're chopping it off at 1 and 4. So 4 is a little distracting, but if you see that's the right hand part of a region, this orange part, then we have this purple down below and this green above here. No, actually, sorry, it goes to this x equals 1. So x equals 1, let me change this color because it's not showing up enough for me. So let me change this to, let's say, something more vibrant. How about red? Okay. So it goes here. The orange is the right-hand endpoint. It goes down to purple and then up red and then across on green. So this is my region right here. It has this bottom part here at 1 and 0.5, 1 comma 1, and then it all comes to a meeting point here at 4 comma 2. That's my region. So I'm going to draw that quickly out there. 1.5 and 1 and 1 and 4 and 2. So I'm going to remember 1, 1 and 4, 2. 1, 1. And then there was like 4 and 2. And there was like 1.5. And I think those are the 3 main points. Yeah, and then we go down and straight and then a little bit of curve there. So down and straight and a little curved here. So that's my region. Now, for this problem, I'm going to read out the rest of the problem, but note, I am not revolving it around the x-axis or the y-axis or any kind of axis. I'm taking this region, I'm doing something very different with it. So let me see what I said here. For each cross section of this region, so let me draw a cross section here. Let's do vertical. It makes it easier. Create a square going up, perpendicular to the xy plane. So you have to imagine this, whatever, this cross section, this rectangle going up into the third dimension. I cannot draw 3 dimensions, but you can imagine this little squarey thing like going into like space. And I don't know how to draw it, but imagine you get a square when it goes into space, right? So it goes up. It literally goes up, right? And so we get a square. A square has the same like length and width, right? So we get a length and a width of the square that's same as this right here, that region. So I get a square there. This slice right here, this cross section it's a smaller like y height there. So when I make a square out of it, this one over here is going to be a smaller square because I'm starting with a smaller like rectangle. So I get a smaller square. And likewise over here on this one, I'm going to be getting the square that size. So each time I go and get a square of that size of the slice in the third dimension going straight up. This sounds crazy, right? Like what the heck is going on here? Why are we doing this problem? I'm trying to show you that the slicing method works no matter what. Even if I make some crazy directions here, we're no longer rotating things. We're just doing some weird cross-section thing. The method is the same. So we need to figure out the stuff for one slice. What are we looking for? We're looking for the volume. So we're looking for the volume for this one slice. So this slice right here that I made into a square. We're going to try to find the volume of that thing. Well, first of all, it has a thickness. The thickness is in the x direction, so we're going to call that a dx thickness. So the thickness of our like square in 3 dimensions is dx. And then what are the other 2 dimensions of the square? Well, the dimensions of the square are this one and this one, but they're the same, right? They're the same dimension because square, right? That's the definition, right? So whatever this thing is going to be the same as the coming out of the page direction. It's a square. Our cross section shape is a square. So how do we do this? We find the volume of a slice, and then we add all the slices together. So what is a slice? Well, the slice is a square. So it's going to be the area of a square. So it's a square times the thickness. We know what the thickness is. The thickness is dx because we sliced it this way. And what is the formula for a square? Well, it's going to be, length squared, right? It's the length squared is how you find the area of a square. This area of a square, sorry, or area of the square times the thickness is going to be what our slice is. So we need to find the length of the square. Well, what's the length of the square? That's this distance right here. That's the length, right? It's the same one, right? That's the size of our slice. So we just have to find the length there and then square it. What is that length? It's a vertical distance. It goes between the top function and the bottom function. So how do you find the distance between two things? You got it. You subtract. So what is this top guy? I don't think I wrote it, but it's square root of x. What is this bottom guy? That's the 1/2 x. So I just subtract those two y values, and that's my length. That's the length of my square. So I'm going to do the y. I'll do y big minus y small, but we know what the big Y is. The big Y is up here. It's just square root of x. And the small y is down here. The small y is 1/2 x. So our volume of a slice is just going to be the big Y, which is square root of x, minus the little y, which is 1/2 x squared, because it's the area of a square, times the thickness, which is dx. And that's the volume of that one little slice. We take a little slice of our region, we figure out the volume of that one little slice. It's kind of funky, but it was a square. So, or like, square with a very small thickness. So we found the volume of that square with a very small thickness. That's this stuff right here. And then to find the volume of the whole thing, we just integrate. We integrate this exact same thing and integrate it from all possible, well, x values, because we're doing everything in terms of x. So what's the smallest possible x in our region? Well, it's right here. This little rectangle right here has an x value of 1. And this x value over here, right, has a very small y height, maybe even a 0 y height, but it has x value 4. So we're going all the possible rectangles, starting from x equals 1, going to x equals 4. And that, my friends, is how you find the volume of this whatever shape, this thing, which is some weird, kind of, a knife looking thing, but it goes in the third dimension, making squares. Some of them are taller squares because the region was bigger. Some of them are smaller squares because the region was smaller. But that's what it is. That crazy shape that I made up. This is the formula for how to find the volume. And then it just becomes, a little algebra problem now, or, just a simple math problem. You just, do all the stuff that you've been doing now for, many, many homework assignments. You're going to have to square this stuff out because, you can't really do it that way. So you can square it out. You get x minus 1/2 x to the, let's see, 1 and 1/2 is 3/2. And you get another one of those. And then 1/2 x times 1/2 x is 1/4 x squared. You can double check my algebra. I think this is correct. So all that stuff there times dx. Find the antiderivative of each one, plug in 4, plug in 1, subtract, get your calculator out. Hopefully you don't make any mistakes. Get your answer, and you have done this problem. All right, well, that has been a very long video doing this, but my goal was hopefully to get you really on board with the slicing method. And the next videos are going to be much shorter because if you got the slicing method, it's the same for the other sections, right? We're going to be doing slices, maybe getting slightly different shapes. As I mentioned before, the next video is on the shell shape. So you get a slightly different shape, but it's still going to be the same process. You're just getting a slightly different shape. Okay, well, hopefully that video was helpful. Hopefully you stayed awake for the whole thing. And if you have any questions, want to do any other extra practice, please reach out, let me know, and I hope you have an enjoyable day.